If you look at an X-ray crystallography map, what do you see? Probably a 2Fo minus Fc. Or maybe you're just seeing an Fo minus Fc difference map. Or maybe you're seeing an omit map. So what am I talking about? I'm talking about electron density maps. So when you see a model in publish one of those pretty pictures of like a protein or something like that, you typically see like a stick figure or a cartoon figure, something with ribbons and curls and sheets and things. Those are all just atomic models. So basically the scientists modeling the positions of the makeup of those protein or that complex based on experimental data. And in that experimental data that you get with X-ray crystallography is something called a diffraction pattern, which is a series of spots that we'll talk about. That then what you do is you work backwards from that diffraction pattern to figure out the electron density distribution. And you get this electron density map, which is kind of this meshy thing that the scientists build the model into. Now, in order to get that electron density map, well, first of all, what is it representing? Basically, when you have to get that diffraction pattern, to get that pattern of spots, what you do is you get your protein to crystallize. So basically get all the copies of a protein to kind of line up in the same shape and freeze. And then you shoot X-rays at them. What's going to happen is those X-rays are going to interact with the atoms in those proteins or in those molecules. And basically they're going to interact with the electrons of those. So atoms are made up of subatomic particles, protons, neutrons, and electrons, and the protons and the neutrons are kind of at like the center of the atom, and the electrons are around them. And the electrons are what are going to interact with the X-rays. And when the X-rays hit the electrons, what they're going to kind of do is they're going to scatter. And so you have these X-rays coming in and then they get scattered. And then those scattered X-rays are going to interact with one another through interference. And so they can either build together, in which case we get constructive interference, or they could cancel out, in which case we get destructive interference. And when they add together, we get a stronger wave, and we call this diffraction. And the stronger wave can be detected on this detector. And then when we work backwards from that detector, we can figure out where the atoms were that caused that scattering. But the problem is that we can only measure the intensity, so we can only measure the strength. We can't measure what's called the phase. So basically, when all these waves are coming together, we can kind of think of it as creating this mega wave. And then our job is to deconstruct that mega wave, which we can do using like a Fourier transformation, which, well, computers can do, but it's like complicated math. But they need more information than we have. They need the phases as well as the intensity. So with the wave, you can characterize it by like its intensity, so its height, as well as its phase, like how in step is it. And we don't have the like is it hitting like this type of thing? Like, what's the step in it? And we don't have that phase information. And so because we don't have that phase information, we can't actually calculate that electron density map, at least not directly. So we have to figure out the phase, which you can do with things like molecular replacement, where you basically take something that looks like your protein and try to like put it in and figure out like how we can orient it in our data to see what our data should look like. And then there's things like heavy atom replacement and things like this I'm not going to get into. But basically somehow you determine some initial phases, but those are going to be like wrong. And so basically you end up with this map that isn't quite right. And then you build models to try to say, okay, well, if I make my model like this, if I build in the atoms like this, what should my map look like? You can calculate kind of going the other direction of Fourier synthesis, try to make that mega wave from those individual atomic model. And then you have to keep going back and forth between that model and the map to see what matches. And in order to help you visualize this, we can use different types of maps where we can show the observed. So this would be including the intensities that you measure, as well as some experimental phases. So that part you already have bias going into that initial map. At least in the case of molecular replacement, which is the most commonly used way to determine phases these days, especially if you have like something that you already know that looks like this protein that you can use. If you're using an experimental method, when you're having to determine the phases like from scratch with some like heavy metal soaking or SAD, MAD, various like selenomethionine, various things that you can do to experimentally, like you have an actual another crystal that you're measuring, and then you're like comparing the two and trying to figure out, because the heavier atoms are going to give a different strength signal and that sort of thing. So you can try to figure out the phases that way. When you're doing the experimental phase determination that way, then you don't have the model bias going into your initial FO. But when you're doing this molecular replacement, because you're starting with a model, you then have this bias built into that initial like your observed data is actually not purely just observed. And then you have the calculated map, where you're actually using the calculated like model that you build and using the calculated intensities and phases. So this would be your FC. So the FO is going to be your observed and the FC is going to be your calculated. Now, what would happen if you did your FO minus FC? Well, this is called a difference map. And here what's going to say is that if you have your observed minus your calculated, if there's something that you observe and that's in your data but it's not accounted for in your model, you're going to get a positive signal. And so this is typically colored green. If you see green, this is telling you that there's something that's missing in your model. Now, what if you see red? Well, here, because you're doing FO minus FC, that means negative, and so this means that there's something that you calculated that isn't actually there. And so then you would see a red. And this can help you then adjust your model, refine your model in order to better fit the data. Now, typically what you're looking at, like how do you know, okay, well, how do I build in this data? Often what you're looking at when you're actually building in this data is going to be, or when you're viewing it, is going to be a 2Fo minus Fc. Now here, you're weighting higher the observed things so that you make sure that you're not over accounting for the calculated, and so that you actually see a signal. So basically, if you do Fo minus Fc, well, now if they match exactly, you're going to see no signal. But if you have 2Fo minus Fc, well, now you're still going to see a signal, and you're going to have the signals cancel out if the calculated is bringing things down. But if the observed, if the values are still really there, you're still going to see a signal, and this is going to be the signal that you're going to be building your model into. And then the difference maps can help you see, okay, well, maybe my model is missing something here, or maybe my model has something extra here. Then you can refine your model, and this is actually going to then help your maps match better to your model and things like this. Now, sometimes there's like, you really want something to be there because you like expect it to be there, or you're really hoping it will be there. Maybe you're trying to solve the structure of a protein bound to a drug, and we call it binding partner or ligand. So in this case, your ligand would be your drug, and you're saying, okay, I really want it to be there. So you kind of make yourself see it's there, like expectation bias. And so this can happen in these experimental maps as well, because these maps are using the calculated, or like they have to have the phases based on your model and things like this. And so if you model something in, then that model something in is going to contribute to your map. And so you have bias going in. What you can do is an omit map, which basically you leave out that part, you leave out that ligand, whatever, and now you calculate the map. And if there is something that, if there's like, your thing really should be there, you're going to see that there's some missing density there, that your observed is showing that there was something there, even though you haven't modeled in that there was something there. And so this is going to be good evidence that there is something there that maybe it's your ligand, maybe it's some solvent or something, but there's something there. And so this is where an omit map comes in. So let's look in a little more detail at how you can actually view these in software like PyMol.
So when the X-rays hit the different atoms, they're going to create these mini waves, and then these mini waves are going to kind of add together to give us this mega wave. And it's this mega wave that we're going to detect on our detector. And through mathematical ways, you can actually deconstruct that mega wave into those mini waves. And if you know the details of those mini waves, then you can figure out the positions of the various atoms. And a way that you can recreate this mega wave is with a Fourier transform. And this is what we'll talk about. But in order to do this, basically you need both the amplitude and the phase. And so basically we can talk about these waves, the amplitude is like kind of how strong they are. And then the phase is kind of like in what step they're in. And this is going to matter because we need that information in order to reconstruct these waves, in order to reconstruct the positions of the atoms. So it can get kind of confusing. And so just a little intuition about what we're talking about. So think about people in a stadium doing the wave. And so when they get hit by those X-rays, they do the electron wave. And so like in the stadium where they stand up and put their hands up and then they come back down. And so each time these X-rays hit somebody, I should say wave, not rave, but then that person does the wave. And these waves are actually spherical, but it's easier to draw them in one direction. But you can imagine that if people are doing the wave at the same time, then their waves are kind of going to add together. But depending on how they might not be doing the wave at the exact same time, because they're going to be hit at different times and they're going to be differently spaced apart. And so if they're spaced in a wave, like an integer of the wavelength, then they're going to add together. But if they're not, then they're going to cancel out. So if they're doing the wave like out of step with one another, out of phase, they're going to cancel each other out. And so each of these proteins is like a stadium full of people doing the wave at different times, leading to this overall mega wave. And the crystal is composed of repeating units of these stadiums. And so what you get is you get this stronger signal, you get this mega wave, and then you need to work backwards from that mega wave to figure out the individual waves. Well, all you can measure is the height of this mega wave. You can't measure the phase. And so if you don't know the phase, then we can't recreate things, at least directly. And so another way that waves can be talked about that might make it easier to understand is to think about them mathematically as in terms of like sine and cosine and things. And so we can imagine if you had a pencil on a string tracing out a circle, and we can do this over time. And so we can think about time or distance. If we were to put, so if every time you go around the circle, you have one wavelength, you're right back where you started. So this would be like in phase. But if you're at different parts, you'd be out of phase. But now if we were to take a picture and we could see where the pencil was, we'd be able to know the phase. But if we don't have that tracer, if all we have is what it drew, well, now we can't tell what phase they're in. And this is the situation that we face in X-ray crystallography, is we only have that intensity information. And so in order to try to figure out the phase, we have to use methods. There are things like molecular replacement, where basically you take something with a similar structure and you try to fit it into your data to try to get the orientation of your data. And therefore the phases. There are things where you can use like heavy metal replacements or selenothionein, or there's various experimental methods you can use to figure out some initial phases. But those initial phases are then going to need a lot of refinement. And so you go back and forth between making a model, figuring out what the signal from that model would be, and then how it matches your data. You go back and forth from this model and the map, refining your model, seeing if it helps the map or makes it worse, going back and forth and back and forth and back and forth. And so there's a lot of refinement that goes in to figuring out those actual phases. And so, but it's important to look at the maps while you're doing this, and the maps are going to help you find your way. So we have the 2Fo minus Fc and the Fo minus Fc, and we'll take a look in a second about how we can actually view these. But the 2Fo minus Fc, this is kind of like the most common map. This is where you would actually see continuous electron density where there should be stuff. And so you're going to build into this electron density. And so you want there to be things there to build into. And when are there going to be things to build into? Well, there's going to be things to build into when your observed signal is going to be higher than your calculated signal. So basically, this is taking out some of the bias from the modeled signal. This FC, this modeled or calculated signal. And so it's weighting higher the observed signal. Now, there are also methods like 2Mo minus minus DFC. Basically, these use some statistical methods to try to more highly weight the things that have a stronger signal. So this sigma, this is like, when we're talking about like contours of the maps, the sigma is kind of like how much, like it refers to standard deviation and how much higher than just like the average signal it is. So if you have a much higher signal, it's much more likely to be real. And so you weight the real stuff, or the probably real stuff, the stronger signals, more highly in these 2M minus, in these like 2MO minus DFC maps. But it's the same basic idea where you're subtracting the model signal from 2 times your observed signal. And so this is going to take out some of the bias from the model, but not all of the bias. But you should still, this should leave continuous signal. So if there's stuff that's modeled that that shouldn't be there, then those regions would get, those regions wouldn't be in the observed signal, so they'll get lower. But if there's something in the observed signal, it'll stay. Okay, so basically that is the 2FO minus FC, but this isn't enough. And so it took out a little bit of the bias, but it doesn't really tell you where you might have issues. And so in order to see where you might have issues, you want to look to a difference map, such as an FO minus FC. And this is going to show you where things should or shouldn't be. So this is going to highlight the differences between FO, your observed signal, and FC, the calculated from the model signals. So if they were to match everywhere, you'd see nothing, but this isn't going to happen. There'll be regions, yes, where they do match, and then you won't see anything. But there are also going to be regions where they won't match, and where they won't match, they can match because they cannot match because the model has extra or because the model's missing something. What we're doing is we're subtracting the calculated, so we're subtracting the model from the observed. And so if we have something in the model that isn't in the map, then we're going to have a negative value. This negative value, we typically color this red, and this is going to tell you that you've modeled in something extra that's not supported by the data. And if you have a positive, this is going to be green, and this is basically saying that the model's missing something. There's something in the observed data that you haven't accounted for in your model. So for example, this structure, you can see that we have this red here and we have this green here. And so you might be thinking, okay, well, maybe this is just swapped and this should be over here. Basically, this is an aspartate, this side chains like this can adopt different kind of like rotational states. They can rotate around this bond. And so they can be over here. This would be one rotamer. This would be over here. There could be another rotamer. And you could think, okay, well, maybe this is just in the wrong rotamer. But then if you were to look at the 2FO minus FC map, which you can see behind it, typically they're overlaid on one another, you can see that you actually have density here in that map. So it could be that you have a partial occupancy where part of the time you're over here and part of the time you're over here. Or it could be that there's model bias going in that made it so that you're seeing this 2FO, this 2FO minus FC map here. So there are different reasons why you might have things like this, but something like that, you often see something like this when you have partial occupancy. And this is actually something that the more complicated refinement thing is that you can actually refine the occupancy. So say like 50% of the time it's here, 50% of the time it's here. Or you can also do partial occupancy with things like if you have like a ligand, like you can say, okay, well, maybe it's bound like 20% of the time. All of this is just trying to help you model most accurately what the phases would be and what your model should be like in order to generate the data that you see. And so the more things that you know, the you can put into your model, but you also don't want to have too many parameters. And you don't want to be modeling in noise, and there's various complicated things I'm not going to get into. But if there are things that you can learn from one of these FO minus FC maps. So if the word of caution though is that you're always going to have an equal amount of red and green because they have to like cancel each other out. And so you're going to see a lot of noise where things aren't really actually something. There's a bunch of other stuff going on in your sample, things in the buffer, various things that could be giving a little false signal. various things that you wouldn't want to actually like model in because they're going to be differing. But you're going to basically get some noise. How do you know if something is real? Well, if something is real, you're going to you should be able to see the backbone. You should be able to see the continuous density with your 2FO minus FC map. And so the continuous density, if I raise the density here, if I raise the contour, then you're going to be able to see there's continuous density out through to this side chain, which is probably why they modeled it over here. So this density is going to be strongest in regions of the protein that are like stiffer and that are more stable, less flexible, and often like the backbone of a protein and the regions in the center. Whereas regions like the side chains, especially of these long flexible amino acids, like this aspartate, these are going to be more flexible, more dynamic. Since they're moving around a lot, they're not going to have like one set spot. And this crystallography is relying on them having this one set spot in order to generate that electron density that you can actually visualize well. And so if it's kind of like waving around and stuff, you can think of it kind of like canceling itself out. And so you're not going to see signal from it. You're not going to see density from it, even though it's actually there. A complicating factor about X-ray crystallography is that that mega wave, it includes contributions from every single atom in your thing. So if you change one thing, you can change everything. And so this can be helpful in that you can be improving your entire map based on fixing one part of the model, but it can also be confusing and various complicating factors I'm not going to get into. But know that when you're modifying that map and things, this is going to be basically the signal that you see is a contribution from every atom that's in there. And so the better you can model it, the better your map can be overall and things like this. Okay, so let's take a look in Primal. So you can also visualize in other software. When we're actually doing the refinement, we often use like Qt. I'm going to use Primal for this, and I'm going to mainly use the GUI, the graphical user interface, because it's going to be easier for me to show things. But you can also do this, everything and more in the command line. But let's go and we will get PDB. We don't just want to get the PDB though, we want to get these maps. So let's fetch 2B3P. We'll get the PDB structure, we'll get our 2Fo-Fc and our FoFC. And we can download this. Okay, so this is a structure of GFP. I'm going to turn on the sequence, which you can just do by pressing the S here. Okay, so you can see that this is the protein. You can also see that there's some like ions and I think there's like various buffer components here as well as the solvent. It can get kind of hard to see things, so I'm going to remove the waters. And I'm just going to manually come in here and delete this stuff so we just have the protein. Action, remove atoms. Okay, so now I have our protein. Now I'm going to color it by B factors. Okay, so when we color by B factor, basically this is saying that regions that have a high B factor or displacement factor, these are regions that are more flexible, more dynamic. They're going to have a less clear density, and they're going to be harder to model into. When we're going to be visualizing the maps, we're going to want to not look at it in this cartoon view, but instead look at it in stick view. So that we can actually see how well things fit. Because when you're looking at it in the cartoon or the ribbon, basically it's showing you the basic backbone layout, but it's smoothing it and things to make it look all pretty. And it's not going to actually show you how well it's fitting in there. So what we can do is we can hide the cartoon, and now we can show as licorice sticks. Okay, so now we are showing this. And you can see that you have these long flexible amino acids out on the edge that are going to be high B factors. And then in the center, you have more of this blue, where we're going to see that the density is going to be better. So how do we actually see this density though? So here, this is where we are going to put mesh on our 2Fo-Fc. and our FO minus FC, our FO, yeah. So our 2Fo-Fc, this is where we should see the continuous density, remember? And so what we want to do is we're going to show the mesh. Often what you do is you show this at about a sigma of 1. And now you can see that it's modeled in. It's because it's not just this crystal, but you have all sort, it's like a crystal lattice. So there's going to, I mean, it's not just this protein, but it's in a lattice. So there's going to be proteins next to it and all of this various things. And so probably want to, like, you can scroll up and down to kind of focus and slice and things like this. You can also do it in here if you were to go to display and then like zoom or clip and stuff. But I'm not going to go into that stuff. Okay, but now we can take a closer look if we want, and we can see that there are some regions where they have really nice density. So you can see here, you're actually able to see inside one of these aromatic rings. You can actually see inside the rings, you have this really nice density. Whereas in other regions, there's going to be worse density, and it's going to be harder to fit things in. But how do you know, like, how to fit things in and which way things might go? Well, one way that you can tell if there's like things that are missing in your model or things that you can add in your model. Now, this is where we're going to be needing that FO minus FC. We need that difference map. Often this difference map is going to be shown at a level of plus and minus 3. So remember that plus, this is like positive. The green, it means that your model needs to have something, that there's something missing in your model. And red means that there's going to be, your model has something extra that's not supported by the data. So for example, this is the site we were looking at before. And so you can see that there's red here, which is saying that our model has more than the map has, than our observed. And the green is saying that our observed has more than the map. And so there should be something here, and there shouldn't be something here. And so why might they have modeled in over here? Well, if we take our FO-Fc or 2Fo minus Fc, so this is where we should see continuous density. But if I have it at a sigma of like 2, this is only showing the stronger signal. And so you can see that you have stronger signal over here. And if we take off our non-modeled, if we take off the difference map, you can still see density over here. But what if I actually decrease the signal levels? This is saying include some of the weaker signal as well. And so if I include some of the weaker signal, say I go to a level of 1, well, now you can see that you have more continuous density into this rotamer over here, like this likely rotamer. So it seems like it's most commonly over here, but you also now you see signal coming out over here, which could indicate this alternate rotamer. And so this is just one example of how you might use a difference map in order to help you, as in addition to your 2Fo minus Fc, in order to kind of fit the model. And then if you adjust, you go in like COOT or whatever, and you manually adjust things. If you change the occupancy, you can hopefully make your model better. And then you calculate the map again and compare them and see whether things fit better. So that's just one example. If you want to know more, I highly recommend this. This is one of my best articles of all time. You're Lost Without a Map: Navigating the Sea of Protein Structures. It's open access, so feel free to go check it out.